Um, all right, so good morning, everyone. I'm Aditya Pandare from Los Alamos National Lab. I'll be presenting our progress on a compressible hydrodynamics solver, which is written on Charm++. So it's an asynchronous distributed memory parallel solver. I'm presenting on behalf of the lead author, Joseph Bokoshi. So to begin with, I'd like to share with you what our objectives were when we started um, working on this project. So we were looking to target highly parallelizable, large-scale computational fluid dynamics applications. So we would be looking at extremely large meshes with um, which were running on tens of thousands of cores routinely. So the use cases, just to give you a perspective, would be blast loading on blast loading effects on on vehicles, re-entry bodies, aircrafts, and such complex structures. The reason I mention this is because to mesh these kind of geometries, which are complex and 3D, we would need to have explicit meshing over all the detail of the 3D geometry. For example, when there's an aircraft, you would have to mesh the entire aircraft in very detail, like the tails, the fuselage, the um, uh, all the other attachments to the aircraft, the payloads, and all that. That's one of the very important things here, because as compared to internal flows, these external flows requires meshes which are a large magnitude larger than the internal flow meshes. So you would have 3 or 4 orders of magnitude differences in these meshes. So we would routinely see meshes such as tens of millions or even a billion cell large meshes. Um, that is why we would like to have an extensive parallel capability in the code. To give you an introduction about the code we are using, it's called Insighter. It's an app in Quinoa, which is built on native Charm++. As an introduction, that's also a compressible hydrodynamics code, which can deal with single or multiple materials. It uses unstructured 3D meshes, so tetrahedral meshes in 3D. So there's a lot of indirect addressing because of the unstructured component. There are a couple of numerical methods in the code.
There's a,
Sorry.
Are you showing multiple slides? We are still on the title slide.
Oh, sorry.
Is it PowerPoint? No, it's somehow not showing the slideshow.
Oh, I'm sorry. Give me a second. How about now?
Yeah.
Okay, so I'll just use this mode. I think the full screen
Yeah, this
is
mode is
not.
fine, I think. Yeah.
Yeah, okay. So like I was saying, we have multiple numerical methods in here: continuous finite elements, discontinuous finite elements, and we also have finite volume methods there. And today I'm going to only talk about continuous Galerkin finite elements. The peculiar aspect about this code is that it has adaptive mesh refinement and adaptive polynomial degree refinement. And this is the fundamental reason why we chose native Charm++ to write our code in, because because of these adaptive refinements, there is load imbalance, and we want to make sure that there is some sort of load balancing strategy to make the code efficient. And I'll show you an example in the later slides to show you the effect of this load balancing. This is an open source code, and it can be found on this website here, quinoacomputing.org. So moving on, I would like to talk a little bit um, about the numerical method that we are using here. The first set of equations here is the ideal gas dynamic equations, that is the Euler equations, and we are talking only about single material flows in this presentation. The numerical method that we are using is a edge-based finite element method, which is basically the same as a nodal finite element method, but the computations are done, or it's cast in an edge-based way, which then makes it very similar to a node-centered finite volume method, which is very well known in the aerodynamics community. Um, so these equations, these Euler equations, are then discretized using this edge-based finite element form. And here I've just shown you the discrete form. What I'd like to point out here is there are a lot of operations over the edges. So inside the mesh, there is multiple nodes, obviously, and the edge that I'm referring to is the edge connecting one node to the other. So there's a lot of operations between these two nodes, which are called edge-based operations. And we would also have operations over elements surrounding this edge, and elements surrounding each of the nodes that constitute an edge. So there's a lot of indirect addressing is what I'm basically saying when I give you all these details. And this becomes important when we're looking at distributed memory parallel algorithms, because we need to make sure that along the process edge, we communicate all the required data structures in a consistent manner. So these are just a few references which point to the numerical method that we are using here. Most of these come from Los Alamos. Um, so now to verify the numerical method that we have implemented, we try out a couple of test cases, and I've shown a few of them here. The first one is a vertical flow. It just makes sure that in the presence of a smooth flow field, so smooth pressure and smooth velocity flow field, we are indeed able to get second order convergence. Second order convergence is extremely important because when we are trying to, practically, when we are trying to simulate a particular flow, we want to make sure that when we refine the mesh, we get closer to the solution that we want to. That is called Lax equivalence theorem. So basically, we want to make sure that when we refine a mesh, we indeed are approaching the analytical or the exact solution. And this problem shown here actually has a mathematically like analytical solution which we can compare with. And on the right hand side on the top here, we have a graph which shows that the method is indeed second order accurate. This slope here is compared with a dotted line, which is the second order accurate line. So we definitely get second order convergence for all the fields that we're solving for. So momentum, energy, and density. So this is a validation for smooth flows. Moving on, we wanted to check something of more practical importance to us, which is a blast wave. So basically, imagine a spherical domain, and at the center of the sphere, we initiate a high energy region. And when the solution is started, the high energy region starts expanding. And we want to make sure that we capture that expanding blast wave in an accurate manner. What is critical here is the strength of the blast wave. So the peak in this density plot and the location of the shock wave, which is also very critical. And here it might be hard to see, but I'm showing density plots here with 4 different meshes. So this is a mesh conversion study in a way, where we try a coarse mesh, which is mesh 1, and we go through different degrees of mesh refinement up to mesh 4, which really approaches the analytical solution, which is the solid black line. And if you can see, the location of the blast wave is pretty accurate in all these simulations. On the right, I show the contour plots, which basically show density and pressure. On the bottom here, I show another mesh convergence. Here we don't get second order accuracy because it's a discontinuous problem as opposed to a continuous problem before. But the point is we get first order convergence when we refine the meshes. So we can again be assured that we can get mesh convergence when we refine the meshes. So we are headed towards the exact solution. That's the important takeaway from this graph over here. So moving on, we have another kind of more complicated test problem where there are 2 things happening now. Here, this vertical line is basically a shock which is going to move over this cavity over here. So the domain is this T-shaped domain that you can see. State 1 is a post-shock state, and state 2 is the pre-shocked state. And this vertical line, that is the shock, is going to propagate towards the right side. And as it moves towards the right, it's going to encounter this cavity. Then that's where some complicated phenomena happen. When the shock moves over the cavity, there is a vertical flow. And then the shock, as it propagates into the cavity, there is some shock reflection and rarefaction waves generated. We want to make sure that the code captures all these phenomena accurately. Here we compare the solution obtained numerically on 4 meshes. So these are 4 different meshes, and we compare it with the experimental results. So these black lines are basically the shock locations from the experiment. And on the top right, we have included solutions from the experimental solutions from the paper. And we can see that the shock locations are pretty accurate. They're not exactly accurate because this paper does not mention the timings correctly. There is some sort of ambiguity as to when the shock actually starts. We can try to match the shocks here and there, but there is some kind of ambiguity uh, as to when the shock actually starts with regards to the experimental time. But what I would like to mention here is that the shock becomes more pronounced. You can see over here it's pretty diffused, and over here for the finest mesh, you can see that it is very well resolved. And similarly, there is a vortex over here, which the blue color gets deeper as you move to finer meshes, which I'd like to show. This is an indication of mesh convergence, basically. So we can capture these multiple phenomena that are happening in this T-shaped cavity domain. The next test case is a even more practically applicable test, which is the Onera M6 wing. This is a standard test for aerodynamics verification codes. I've shown the mesh here, or I've shown only the surface mesh here actually. And on the bottom is the computations on one of the meshes that we have tried this out on. These are pressure contours that I've shown here, and on the next page, what we want to see is whether we can compare with the experiment. So the experimental data has been taken on different locations on this wing, different span-wise locations on this wing, and we are comparing the pressure coefficients. So we would like to compare with experiments and to make sure that um, we can compare well there. So these are the 6 different locations on the wing, and the drop here. So I'm going to zoom in on one of these. Let's zoom in on this one, for example. So we see 2 meshes here, a coarse and a fine mesh, and the experiment is shown in the red crosses. So you can see how pretty much everywhere the simulation is matching with the experiments well, but near the shock location is kind of off, and that could be due to a couple of reasons. We don't include viscosity in these computations, because of which the shock is it's even smeared. As you can see, the shock is not a sharp vertical line, and that can happen because in viscous flows the shock is obviously smeared. And but regardless of that, we get good agreement with the experiments at all span-wise locations. This is another location at 90% of the span, and we basically want to see that we are getting good agreement with the experiments. So now that we have done some basic verification studies and that we are getting good validation from experiments too, we wanted to do some optimization of the code so that it's efficient. And this slide basically shows that most of the heavy computations were happening in the right-hand side part of the algorithm. The computation of the right-hand side takes like 91% of the time. And when you go further fine-grained, we can see that there are the gradient computations, the domain computations, and the source term computations, which take up most of the part. So this is how we decided which part of the code to optimize to get a better performance. And this slide is basically a summary of what we did to get a good speed up. So basically we got a 6x speed up starting from the baseline code. When we went on optimizing the code, we got up to a six times speed up. And the most important things that I would like to mention is we replaced all the tree-based data structures like maps and all those with flat data structures which could be streamed and which had contiguous access. And basically we changed the loop accesses from maybe node-based loops to edge-based loops, or maybe element-based loops to edge-based loops, and such. And that actually got us a lot of computation efficiency gain. And that's what this slide basically talks about. After this, excuse me, after this optimization, we did a strong scaling study on Lanel's Grizzly supercomputer, and The light blue lines are the edge-based finite element algorithm that we will focus on. And there are two light blue lines. One of them is the non-SMP mode, which is the one on the one with the hollow markers, and then there is the SMP mode down here. After the optimization, we got really good scaling for both the SMP and the non-SMP modes. After a point at around 28,000 to 30,000 cores, we saw a plateauing, basically saying that we had reached the sweet spot and we shouldn't go any further. We are throwing too many resources at the problem. So we definitely get very good scaling. And the other lines here, which are the yellow and the green lines, show the other numerical methods like discontinuous Galerkin and the other continuous Galerkin frameworks, which also show very good scalings on thousands of compute cores. Now, since we have good strong scaling, the next step was to see parallel performance when the load imbalance was triggered. And the way we computed the load imbalance, or the way we induced load imbalance in the problem, was for the set of blast wave. So basically, when there was a blast wave where the density exceeded a certain quantity, there was some extra physical computation that was triggered. And this computation caused load imbalance in the vicinity of these partitions, basically. So here you can see at different time steps how the blast wave progresses through the domain. It kind of expands, and because of that, the extra computation, the zones which have the extra computation, that also goes further ahead. And clearly the green line shows the extra computations without any load balance. So the grind time, which we should try to be as constant as possible for the grind time, that goes on increasing. When the load imbalance, when the load balancing is triggered, and there are a couple of load balancing we've tried here, we can see that this is actually pushed down and the load imbalance is eased, and we get better distribution of resources. And just to compare, the black line on the bottom here is without the extra computations, where it's very uniform load, and the other lines basically show how when the extra load is triggered, how the load balancing works to ease the computational load imbalance, basically. So this was actually a very promising result that we saw, and we have good hopes from the algorithm that we have implemented. So with that, I end my presentation. We are working on different fronts on quinoa basically right now. There is a multi-material algorithm that is being implemented. It has a finite volume and discontinuous Galerkin numerical method for multi-material flows. We have p-adaptation that's going on, which also induces load balancing. There's a productization SBIR with the CharmWorks folks that's also going on. There's a 3D mesh-to-mesh transfer, which is actually what the next talk is about, where there's the target applications there are basically fluid structure interaction type of flows. So basically with that, I end my talk, and I'm open to questions. Thank you so much.
All right, Justin, back to you. Questions?
Were there any questions? I didn't have any immediately.
I have one, but I'm on my phone and I can't figure out how to put my hand up.
That's okay, you can ask.
So what load balancing strategies are you using in this case?
We are using greedy com, and well, we are using a couple. Give me a second. Let me share my screen again.
Yeah.
Can you see it?
Yep, there it is. Perfect.
Okay.
Thanks.
So we have tried a couple of things. There is a 10x over decomposition, so 10 times more chars than the CPUs. We've tried that, but that doesn't give us as much better performance as 100 times. But then in the 100 times virtualization, or 100 times over decomposition, we use greedy.com, distributed, and neighbor.
Okay. And can you remind me again how many cell elements you have per char? I if I remember correctly, you have multiple per char, but maybe that has changed.
We definitely do have multiple per char. Give me 1 second. So I'll have to look, but it's probably per char of at least like 10,000, something like that.
Oh, wow. Okay. Okay. So
Hang on, but that's for per char, I would say a few thousands because there is a 100x over decomposition. So a few thousand. Yeah.
okay.
It's the 100x is very unusual though. So probably we should talk about why you needed 100 and why 10 did not work. And also, is this with SMP or no SMP? Are you using separate for the rest of the people's benefit? Are these charts being run on each core? SMP or no SMP?
I'm not sure about this particular run, but we have tried both, but I'm not sure about this particular run. I'll have to check about that.
Okay.
But to just to comment that 10x doesn't work, it's not like it doesn't work, but the 10x line is over here. It does the job, but it doesn't do the job as well as a 100x over decomposition, if that makes sense.
All right.
Yeah, I wonder. And it's unstructured meshes, right?
Yes.
So some of it could be cache performance, but then that would have shown up even on the left without, yeah.
Right. It would have shown up even with the no extra load over here for the black line, and even before the 100 time steps in this zone. Yes.
And when you say extra load, how heavy does an object become? Have you looked at it? Does it become much heavier?
I think the load was made pretty heavy so that this difference is very pronounced, you know.
Oh, I see.
But again, I would have to talk to Joseph about that.
Okay.
He's the one who did this run. But we can talk about this more when.
Okay. No, but I think if the load variation is like that, then one can probably write some math about how much virtualization you would need for different types of this. And in fact, probably in this situation, it may be better to split, dynamically create new chars rather than let's start with a very large number. But interesting options. Okay.
Right. That's a good point. We should actually see what the simulation was run with. And yeah, some back of the envelope calculations should definitely be done. I wonder if Joseph has done this. I'll ask him for sure.
I have another related question. If you have a uniform load distribution, or roughly uniform, so you don't add this extra load, do you know how close the load balancers are able to get you to basically a space filling curve so that communication overhead is really minimal compared to computation? Have you done studies like that?
We have. So basically you're saying no extra load, but turn on the load balancer regardless and see the overhead, right?
Well, no, not the overhead of the load balancer necessarily, but Francois Hébert will talk a lot about this later. But basically, if you to see if the load balancers are able to bring down to put chars that frequently communicate with one another on the same node, whether you've been able to get it to do that in practice.
So now you're talking about SMP mode though.
No. A regular, even without SMP. There are many chars on each core even. The question is, are they nearby ones?
Okay, I haven't seen that.
Greedy will tend to ignore that communication and they'll scatter them around.
Right.
Yeah, because I don't want to say anything of what Francois Hébert is going to talk about, but this is where we started, and that's why I'm interested if you've had any experiences with it, because we want to make sure that sort of our baseline performance is as high as absolutely possible, and so I'm curious if you've kind of measured baseline.
That's a good question. I have seen some results with I've seen some of this with the DG methods. This is continuous finite element, but I have seen some results with the DG method, which probably can be extrapolated to this one. It does try to bring different chars onto the same node or closer, basically. But I will have to verify that. It's been a
Okay.
while since I looked at that, but we should talk more. I'll definitely verify that for you.
Yeah.
We should wait for the cosmology talk from your group, Nils. But I should say that when communication is important, greedy is not a good strategy to use. And there are the other strategies kind of fallen behind a bit, but we need to bring back the prefix-based what do you call it, the space filling curve based ones, or graph partitioning Parmetis based ones, and so on, that actually don't use Parmetis for the mesh, but for the objects. So it's much faster. So there is a variety of strategies possible. And our attempt, I think, in the Charm community is to try to make that as automatic as possible and increase the suite of strategies. And then remember, I think this is kind of a longer comment than needed, but Harshita's thesis a few years ago used a machine learning model to collect application characteristics and then decide which strategy to use. And that was in operation until recently, but I think with the new load balancing framework, we need to bring all the strategies forward into that and then redo the machine learning calibrations again for it. But the attempt long-term will be, you shouldn't have to think what's the right strategy to use. But in the meanwhile, we need all the nice new strategies.
As a follow-up to your question or your comment, you said parameters. Would that be replaceable with any other domain decomposition software or library?
Yeah.
Okay.
Scotch will be fine, or your Trilinos has
Zoltan.
Things. Yep.
Yeah,
But
okay.
remember, it's an object communication graph we are talking about, not the mesh. So
Right.
It's much. It's just tens of thousands rather than millions or billions.
Right.